All right, y'all, we are continuing on. This is notes 1D, and this is kind of a continuation of the last lesson. So if you remember in the last lesson, we were talking about describing what our distribution looks like, and we use this acronym SOX. And so this first one was shape, and we did this in video 1C. And then this is outliers, and also with outliers is anything unusual. And we hit on this a little bit in 1C as well. Center, and our center is our mean or our median. And this was also in 1C. And then our last one is our spread. And we're going to do this one in 1D, and then we're going to go up here and we're going to look at outliers again. Okay, so that's kind of an overall thing of where you can find this stuff. Okay, so spread. So spread can also be said, we can say variability, we can say the variance in our numbers. And so the three ways that we're going to see this most often is our range, and our range is it is our max minus our min, and that gives us our range. You know range clear back from elementary school. Okay, so range is the difference, max minus min. Okay, now range is a number, it's not an interval. That's important. Range is a number. So we would say the biggest value minus the smallest value is going to give us a number. Okay. The next one that we have is standard deviation. And I don't know what your history is with calculating standard deviation. So I'm going to show you how to do that, and we're going to do some standard deviation before we actually get it on the calculator. And then the last one that we're going to talk about is something called an IQR. Okay, so standard deviation, that's this first one that we have here. So standard deviation, what is that? It is the average deviation of an observation from the mean to the data set. Okay, so basically, we're going to walk through this example, and I think it makes more sense because you will probably never have to do these by hand. You'll always do these on the calculator, but it's good to do one by hand just so that you kind of know where the numbers come from. And so another way to look at this is how much does the data deviate or variate, right? How different is it from the mean? I use that word deviate. My kids are going to think I'm saying devious. They're just looking at me right now. Okay, so I have this example. So I have an elementary school children were asked how many pets they have. Here are their responses, ranged from lowest to highest. I have that backwards. Should be ranging from lowest to highest. So we had somebody that had one pet and somebody who's got a zoo. They got 9 pets. All right. So if I look 1, 2, 3, 4, 5, 6, 7, 8, 9 children. So my n value here is going to be 9. Okay. So first thing I want to do is calculate the mean. So we know how to do that. We're going to plug in all these numbers and then divide by 9. So oh, and look at that. It's a nice number. So I added it all up, got 45 divided by this. So I'm going to say x bar equals 5 pets. Okay, so now it's going to be this deviation. So if this is the mean, remember how much does the data deviate from the mean? So if this is the mean, and this number right here is 1, 1 minus 5 is going to be negative 4. 3 minus 5 is negative 2. 4 minus 5 is going to be negative 1, negative 1, negative 1. 5 minus 5 is 0, so no deviation. And then this is going to be 2, 3, and 4. Okay? And so now what we're going to do is we are going to square this deviation. So if I have negative 4 squared, then this is a positive 16. Now, the whole reason that we're squaring it is because we don't want negative numbers. If I have these negative numbers and these positive numbers, well, they're going to start canceling each other out, and that's not what I want to do. So all of these are going to be squared, and when they square all of these, I'm going to get positive numbers. Okay, so what we say is we have this sample, and we have all of these deviations that we take, and I have x, so my first value, my first data point, which would be x1 minus x bar, so minus the mean. So what I've actually got down here then is that data point minus the mean squared. So what this is saying is if this was x, if this I is data point 1, I would have 1 minus 5, which is negative 4. And then this is data point 2. So 3 minus 5, which is negative 2. All right? So I end up with this table of data. So now we will compute the average squared deviation. But really, that's kind of what we're doing, because what we're really going to do is we're going to, instead of dividing by the total observations, we're going to divide by this number n minus 1. And so what happens is I have this sum of my standard deviations, my squared deviations, and I'm going to divide this by n minus 1. And so what this gives me is if I add these up, which let me do this real quick. So I've got 58. And I have 9 total observations minus 1. So 58 divided by 8 is going to be, oh, hold on. I think I did something wrong. Let me add that up again. 16 plus 4 plus 3 plus 4 plus 9. 52. This should be 52. So 52 divided by 8. There we go. 6.5. Always check me, because I tend to make mistakes. All right, so here's what I have. What this is saying is that this value of 6.5 is called our variance. So this value, 6.5, is called our variance. And if you look at this, this variance is s squared. This is the average squared deviation from the number of pets of these elementary children, okay? But because this average is squared, our units are in pets squared, and that doesn't make any sense. So what we want to do is we want to take the square root and get back to this. So if I have the variance, and the variance is 6.5, and I take the square root of 6.5, then this is going to give me, the square root of 6.5 is 2.55 pets. Now, let's just look at this for a second. If we look at this data, right, and we know that our mean here is at 5 pets, so this is my mean. If I ended up with 6.5 here as my variance, that doesn't make any sense because these numbers are not that far away from this. So what this value of 2.55 is telling us is that the average standard deviation from this is 2.55. These numbers are only 1 away. That's not bad. But this number of 9 is quite a bit of ways away. Okay? Now, I'm going to show you how to do this on the calculator so that you don't have to go in and subtract all of these values and then square it and then take the square root. So I'm going to show you another way to do that. But let's talk a little bit more about standard deviation for a minute. So our variance formula is s squared sub x, which means we've got some value that's in there. And this formula is the sum of all of our values subtracted from the mean squared divided by n minus 1. So let's identify this. So the symbol for variance is s squared x, and mean doesn't change, that's x bar. And the individual observations don't change, that's x sub I. Number of observations is still n. The capital sigma, which is this guy, that means we're just going to add it up. And our symbol for standard deviation, this is variance, but our symbol for standard deviation is just s sub x. And this is where we need to be. That's the important one. So because we have all of this, this is like saying if I want s sub x, I'm going to take the square root of this guy. Now, this is not something that you're ever going to have to do, I promise you. And so what we say here is that if I have the square root of all of this, that this becomes the standard deviation. Now, just in case you need it, this is on the AP formula sheet. You're going to get a formula sheet for the AP test, and this is on there. If for whatever crazy reason they want you to calculate the standard deviation. Usually your calculator will do it for you. Okay? So now, this is the part that we have to do on the AP test, and that is interpret the results in the context. So, when we do this, we would say the number of pets typically varies from the mean by 2.55 pets. It measures the typical distance of the values in a distribution from the mean. Okay? So, standard deviation should only be used when our center is mean. So, if you remember what we did in the last lesson, we said sometimes we don't use mean, sometimes we use the median. And remember, we use the mean when there are no outliers. So, if there are no outliers in the data and we want to find a variance, we're going to use standard deviation. So, if there's no outliers, we use mean for the center, and we use standard deviation, which is also abbreviated S of x. So this is standard deviation for the variance. How much does our data vary from the mean? Okay, so just a few little key things about standard deviation. It is always positive. It's always a positive number. So the values might look like they're negative. If we look at our pets example here, we have more variance on the low end of pets than we do on the high end of pets, but we would never have a negative standard deviation. It's always positive. The standard deviation is 0 when all values are equal. And that would be if you had this scenario. Let's say everybody in the room said, I have 2 pets, I have 2 pets, I have 2 pets, I have 2 pets, I have 2 pets. Well, my mean is 2, and the variance from the mean would be 0, because everybody has 2 pets. So when all of the data is the same, then your standard deviation is going to be 0. Standard deviation has the same units of measure as the original variable, so you have to do that. So our standard deviation up here is 2.55 pets. You've got to have the unit on there. Standard deviation is non-resistant, okay? Which means that outliers make our value large. It makes our standard deviation large, and we don't want that. That's why we use the mean for centers and we use standard deviation when we have outliers, okay? The greater the standard deviation, the greater the variation in the distribution. This means, so the greater the standard deviation, then that means for the values, so let me put it this way, values are farther from the mean. Okay, so if I had something that looked like this, if this was my mean, and I had data that was clear down here, and data that was clear up here, this standard deviation would be different if my data looked like this, right? So this was 1, 2, 3, 4 away, and this is only 2 away. Okay, so this would have a smaller standard deviation, and this would have a bigger standard deviation. Okay. All right. So if you remember, I said we can use the range, we can use standard deviation, or we can use this thing called IQR. And IQR stands for interquartile range. And what we use with IQR is that we are going to describe the spread, and we're going to use percentages. So we use percentiles to measure the percent of an observation that falls at or below or above a value. Okay? So if the median is in the middle, then this would give us 50% below and 50% above in our standard deviation. Okay, so the reason why we would use this is we are going to use this if we are using median as our center, then we use IQR for our variance. So if we're looking at percentiles, and I say, okay, here's my median, this is in the middle, I've got 50% that's above, and I've got 50% that's below. And so if I have an outlier, it's not going to shift the data because these outliers are going to cancel each other out because you still have 50% of the data above or below. Okay? So let's look at this. When we're looking at our percentiles, we have this 0 percentile. And the 0 percentile is going to be the lowest value in the data set, and we are going to call that our min. The first 25%, so this is the 25th percentile, we are going to call this the first quartile. It's not a quarter, it's a quartile, and we abbreviate this Q1. So 25% of that data is below that value. The 50th percentile is going to be our median. It's right in the middle. Okay, now technically, this is Q2, right? If this is the first 25%, this would be the second 25%, but we don't use Q2, we use median. And then the next 75%, we call this the third quartile. And we abbreviate this Q3 for the third quartile. And then the 100% is going to be our maximum. Okay, now these 5 numbers right here, the min, Q1, median, Q3, and the max give us something called a 5-number summary. 5 numbers, okay, 5 numbers. So we're going to calculate these by hand, and then I'm going to show you how to do it on your calculator next time we get together so that we can make it quicker. So here is the data from a previous AP Stats class. They were asked how many hours of sleep they got before the first day of school. So here is all my data, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So I have 22 students. This is my n value is 22. So if I take 22 plus 1, I end up with 23 divided by 2. And if I have 23 divided by 2, this is going to be 11.5. So my average is going to be between my 11th and 12th data point. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Uh-oh, I lost count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 and 12 are right here. Okay, so this value right here is my median. And my median then is going to be 7. So I don't have to take the average of those two because 7 plus 7 divided by 2 is going to be 7. Okay. All right, so the next thing I'm going to do is I'm going to find my Q1. So my Q1 is going to be from my median. So my median is right here. So it's going to be everything this direction. So I can count these up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 data points. Now, I included the 7 that was right here. Okay. So 11 plus 1 divided by 2 is going to be 6. So the 6th data point, 1, 2, 3, 4, 5, 6, this is my 6th data point. This is going to be my Q1 value. Okay, now don't get hung up on the fact that this is a 6 and that's why this is a 6. No, this is the 6th data point. So 1, 2, 3, 4, 5, 6. That's where the 6 comes from. Okay, we know what our min is. Our min is 2. That's the smallest data that I have. And now I'm going to find my Q3. So my Q3 is the average that's of these numbers. So if I'm going this direction, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So again, if I have this value that's 11, it's going to be the 6th data point from my middle. 1, 2, 3, 4, 5, 6. It's this one right here. So my Q3 value is going to be 8. Let me go through that again. So I know I have 11 data points on this side, and I have 11 data points on this side. So this is the 6th data point. So for the lower quartile, I counted from my first point. But for my Third quartile, I'm counting from my median. So 1, 2, 3, 4, 5, 6. So that value there is 8. And then my max is 8.5. So this is my 5-number summary. All right, we're going to create a box plot here in a minute on what this looks like, but this is how we're going to get this data. Okay, now our IQR is the range of inner quartiles. So what this means is I have Q3 minus Q1, and that is going to be a single value, and that's my IQR. So if we look at this value, I have Q3 minus Q1, so I have 8 minus 6, which is 2. Now, 2 what? This was the amount of hours of sleep that they got before the first day of school. So this is going to be 2 hours. Now, what this is saying, remember, is that this is 2 hours is the range here where my data comes in by variation from my median. This data is only going to be 2 hours. And I know you're like, okay, well, this goes all the way down to 2, but that's not what it's saying. It's saying from inner quartile to inner quartile. So Q3, this data right here is going to be only 2 hours. Now, if I create a box plot, I'm going to show you how I come back to some of these numbers. So a box plot takes this 5-number summary and we look at it graphically. So here's what I'm going to have. I'm going to create hours of sleep. So here are my hours of sleep. And I'm going to plot these 5 numbers. So my min is down here at 2. So this is hours of sleep. And my min gets a dot. So whenever we plot the minimum, it's going to be a dot. And my maximum is also going to get just a dot, and that's 8.5. So I'm going to put a dot right here at 8.5. Now I'm going to create a box. This is called a box plot. So I put one line at 6, one line at 7 for my median, and one line at 8 for my Q3. And then I connect all of these and make a box. And this is my box plot. And then I connect my box plot with 2 lines. These lines should be at the same level. They're not. So I'm sorry about that. Now, here's what this means. From the min to Q1, so this is my Q1, this is my median, this is my Q3, this is my max, and this is my min. Okay? So here's what I have. From this dot to this line, it encompasses 25% of the data. It's my first quartile. From Q1 to the median, this is another 25%. This is another 25%, and then this is my last 25%. So I have 25, 50, which we said the median is 50% of the data is before it, 50% is after. This would be 75% of the data, and then 100% of the data. So if we go back up here and look at our IQR, we're taking Q3 minus Q1. So what we're saying is that the IQR encompasses 50% of the data. So everything that's in my box, so your IQR is 50% of the data that's in the box. So that's really important that you see how that all kind of goes together. Okay? All right, let's look at outliers now, I think. Yep, that's what's next. Outliers. So what I have here is using our 5-number summary and the IQR, we have a special way to determine if something is an outlier. So what we've seen so far is we have data that maybe looks like this, and then we have something here, and maybe we have something up here. And what we're saying is, well, this is an outlier, and this is probably pretty sure an outlier, but numerically we don't know what that outlier is, okay? So what we do is we take we create this thing called the outlier test. So you have to have your 5-number summary, and then you have to find the IQR. So remember, that's Q3 minus Q1. And then we're going to use this formula. So compute Q1 minus 1.5 times the IQR. And this is anything that is below that number. So we would call this our lower outlier. And this one, where we're adding to Q3, would be our upper outlier. Okay, so we're going to use the sleep example that we just did on the other page to see if we have any outliers. If we look at this data on here, 2 is like not very much sleep at all, and we've got all these people right here at 8.5 hours of sleep. So this data doesn't look like an outlier, but this guy, I don't know about him. He might be an outlier. So here's what we're going to do. So we're using the sleep example, and we just calculated our IQR, and we said our IQR is 2. So if I want to find the lower boundary, it's going to be Q1 minus 1.5 times IQR. So my Q1 number was 6. So 6 minus 1.5 times 2. Okay, now if I plug this in my calculator, I have 6 minus 1.5 times my IQR of 2, which is 3. So this tells me that 3 is the lower limit. Well, if I look back at my data here, I have this number 2. So 2 falls below 3. So I can say here that 2 is would be a lower outlier. And I'm going to say because, and I should say 2 hours of sleep, there's my context, 2 hours of sleep is a lower outlier because it is less than, remember, less than, greater than, those are super important, less than 3 hours of sleep. Okay, now I'm going to find my upper. And that's going to be Q3 plus, I want to see anything on that side of 1.5 times the IQR. Okay, so for this one, my Q3 is 8. So I have 8 plus 1.5 times 2. And if I plug that, 8 plus 1.5 times 2, it says 11. So anything greater than 11, so this is my upper limit, anything greater than 11 would be an outlier. And if I go over here, my biggest data point is 8.5. So I can say I have no upper outliers. And I can even say because all sleep hours are less than 11 hours. Okay, we're not going to take the time to actually go through all the math on this, but sometimes you have something called a modified box plot, and I'm just going to show you what that looks like. So if I take this data, I now know that 2 is an outlier. So okay, so my data, this is still 8.5, so this is still my max. And nothing else changes. 6, 7, and 8, those are my quartiles. Okay, so this is Q1, this is my median, and this is Q3. And now, if I flip this guy over, my lowest number that I have for sleep hours is 4.5 hours. So I'm going to take at 4.5 hours, right here, 4.5 hours, I'm going to put a little dot. And then I have to go over here and I'm going to put an asterisk on 2. And this asterisk on 2 says that it's an outlier. And that's what a modified box plot would tell you, is that because I have this outlier, it's not played into my graphical representation anymore. Okay. All right, I'm going to give you some cheats on what this looks like. So the shape of a distribution versus the shape of a box plot. So if we have something that's symmetric and uniform, that would be something that would be a distribution that would look, I don't know, like this. Oop, not like that. Sorry, guys. something that looks like this. All very similar, all very close to being the same. So my box plot for that is going to be very equal. So if this is 25%, then this is 25%, and this is 25%, and then this last little bit here is going to be 25%. So these are going to be all even. If I have something that's symmetric but bimodal, then that means I could have something that, that looks like this maybe. Right? And if we looked at this with a rolling graph, it would look like this. Right? So this would be something that's bimodal. And if I have something that's bimodal, it looks more like this. And this is going to be a big box. So these little parts on the end are still going to be 25%. Everything's still 25%, but this box is much bigger than it is here when it's even. Okay? If I have something that's symmetric and unimodal, so we said symmetric and unimodal is going to look like this. This is going to be a very famous curve that we're going to spend a lot of time dealing with. What happens here is I've got these long, remember I've got this long potential outliers that I have out here. So I have these long whiskers. I've got my box here, and then I have these long whiskers on the end. So I have long whiskers. And that's what these little lines are called. Sometimes the box plot's called box and whiskers plot because we have this. So this bell-shaped unimodal is going to have these long whiskers. If I have something that's skewed, so this is skewed left, so this over here is my tail. So this is left skewed, then just probably like what you would think, it's going to look like this. That means I've got data that goes way out here on the left. And if it's right skewed, it's going to do the same thing, right? So here's my tail that goes this direction, and my box plot will look like this. Okay. And then I've given you some little hints here. This is when the mean is less than or the mean is greater than. We did that in our notes the other day. Okay. Let's see, I think we're at practice. Okay, cool. All right, so we're at group practice now. We're going to practice all this stuff together. If you were not in class, then I'll go ahead and fill these notes out, but I want you to do this independently, and then you can come back and check your work. Okay? Thanks.